So now, before we go into the kind of the depths of where this takes us, I want to do one concrete example. So I'll show you an actual example of a problem reduction between two problems, or from one problem to another. So here's what we'll do. We'll take the problem one to be our kind of canonical simple problem that we've been talking about so far. So P1, problem one, answers the question: does a given array have an element in it that's greater than or equal to a threshold m? Okay, so an instance of P1 is specified by an array and a threshold. Okay, that's what makes an instance of P1. So anytime you have an array of numbers and a threshold number, that's an instance of P1. And by the way, if you understand all this stuff, right, if the idea of problem reduction feels very clear to you, then skip ahead by all means to the next video, right? This is just going to be an example of how we would think about this. Anyway, so there's problem P1, super simple problem. And we know problem P1 is in P, right, by the way. So we already know that this is a tractable problem. Problem P2, however, we'll define to be the decision version of the knapsack. So when we've used the knapsack problem before, when we've looked at the knapsack problem, we've looked at the optimization version, right? So the optimization version that we're all familiar with says, here's our items, our weights, our capacity. Now go find the best subset, right? So the optimization version says, optimize the value function for this problem. The decision version is subtly different, okay? So the way the decision version works is it says, right, so this is the decision version, it says, given items, given weights, is there a subset of those items that fits in the knapsack with a value at least k? Okay, so the decision version of the knapsack is exactly the same as the optimization version of the knapsack, but it also has this threshold k. So it's asking a question of existence of a subset. It's not explicitly trying to find the best. It's just asking, does there exist a subset that has, you know, a total value of at least k that fits inside the knapsack? Okay. So here's our goal. Given those definitions of P1 and P2, let's design a polynomial time problem reduction from P1 to P2. All right, so what does this mean? Well, this means we need to convert instances of P1 into instances of P2. Okay, so that means if I give you an array and a threshold, right, there's our array and our threshold, then you need to generate, this algorithm or this reduction needs to generate an array of values, an array of weights, and a capacity and a threshold k for the knapsack problem, right? So you take an array and a threshold for our array search problem and generate an instance of the knapsack problem, which means you generate a value array. This value array could be any length, right? Could you generate a weight array? The only constraint here is it needs to be the same length as the value array, a capacity c, and a threshold k, right? And these could be anything. The only rule is that if I give you an instance of problem P1 that is a yes instance, then your problem reduction had better generate an instance of the knapsack problem that is a yes instance. And vice versa, if I give you an instance of P1 that is a no instance, the reduction better generate an instance of P2 that is a no instance. Okay, those are our rules, right? They have to be valid instances, and they have to have the same kind of the same output associated with them. So here's an example of a problem reduction that does the trick. Okay, so here's how it goes. So our reduction one, let's call it red one, takes in an instance of the array search problem. That is, it takes an array and a threshold, and then it does the following. So for each element of the input array, it associates an item in the knapsack problem. Okay, and the item's value will be exactly the number at that position in the array. Okay, so it's going to say here's our value array. Well, each value of these items is just going to be the number that sits in the input array. Okay, and this input array, that's the array that we're searching for something that's greater than m. Okay, so each item is associated with exactly one index of our input array. Now every weight of the items is going to be 1. Okay, so what's the purpose of this? Well, we're going to set our capacity of our knapsack to 1. So this means that exactly one item fits in the knapsack, right? We can take one item. We can't take 2, right? Because every item has the same weight, has a weight of 1. And we will never just take 0, right? Because it'll be better to take something than nothing. And then what's our K? Our K is going to be the threshold. Okay, so the threshold on the knapsack will be the same as the threshold for our arrays. And so then what this algorithm will do, remember this algorithm isn't solving any problems, it's just converting from one problem to another, right? So it returns just this instance of a decision version of the knapsack. Okay, so the first question is, does this reduction create a valid instance of the decision version of the knapsack problem? And of course it does, right? It returns us values, weights, capacity, and threshold, right? So if I have those 4 things, it's a valid instance of the knapsack problem. So we're good to go there, right? So that's a check mark. So check on this. So what's our second question, all right? The second important question to determine whether this is a sensible problem reduction. I'm going to move that check mark because there we go, perfect. It's in my face, tickling my nose. So the second question is, if I give it a yes instance of the original problem, does this reduction give me a yes instance of the second problem? And it turns out the answer is yes, and here's why. So suppose there is an element of our input array that exceeds the threshold, right? That exceeds our array threshold. That is, suppose this is a yes instance, and the index which shows that it's a yes instance is j, right? So at index j, the value there, or the number in the array is at least m. Okay, well that means that the value of item j in our output knapsack problem is that, right? Which is greater than or equal to m. Okay, so that's greater than or equal to m. Okay, the weight of that item is 1, because the weight of every item is 1. And since the capacity of the knapsack is 1, that means item j fits in the knapsack. Okay, so this is a valid subset, right? It is a feasible subset for our knapsack problem. Okay, so because we've set our knapsack's value threshold to be equal to our array search value threshold, we know that the value of this subset is at least m, right? Because it's a yes instance of the initial problem. And so that means the value of this subset, when we put it in the knapsack, has a value of at least k. Okay, so what do we have? We have that if there is a yes instance of our array search problem, this reduction converts that into a yes instance of our knapsack problem. Okay, so that's question number 2. Question number 3 is exactly the opposite. Does it take no instances and map them to no instances of the knapsack problem? Okay, so what does it mean for our problem 1 to have a no instance, to be a no instance? Well, if it's a no instance, then that means that for every index, right, for all indices for this array, the value or the number in that index of the array is less than m. Well then, what do we have? Well then, for any index, for any item now in our knapsack problem, the value of that item is less than k. Right? Why is that? Well, because k, we've set k to be equal to m. So what does this mean? We know already that the only subsets that fit in the knapsack are the singletons, right? Are the ones that have only one item in them. And so this fact here means that every feasible subset for our knapsack problem has a value strictly less than k. What that says is that there exists no subset, no feasible subset with a value of at least k, which means that the knapsack problem is a no instance. Okay, so what do we have? Well, we've got some kind of a process. It turns out it's a linear time process for converting the array search problem into the knapsack problem. And it converts yes instances into yes instances and no instances into no instances. So what does this tell us? Right? Remember, if we have a polynomial time problem reduction, What that tells us is that if the second problem is in P, right, if the problem we're reducing to is in P, then the problem we're reducing from is in P. Right? But this is kind of a trivial one because it takes a problem that is in P already, right? We know the array search problem's in P, and it reduces it in polynomial time to another problem. All we know at this point about the other problem is that it's in NP, right? So we don't have a proof yet that the decision version of the knapsack problem is in P, and so this problem reduction doesn't really get us much, except to illustrate how a problem reduction could be performed. But nonetheless, there's your concrete example of a problem reduction.